Thanks very much, Paul-André. So first, I need to apologize for two things. First, I was not here yesterday or on Wednesday. I'm sorry, I had another kickoff meeting yesterday, but just my research team start of year meeting all day long, and I was teaching all day on Wednesday. So I'm sorry I missed all the previous talks, and so I hope I'll be on topic for this workshop, but I cannot be sure because I missed the beginning. And the second thing I want to apologize for is, I'm very interested in the topic of the Malinka project, but I don't have anything new to say about this. I have things to say, but I was already saying the same thing, say, 1 year ago, so I know there are a couple of people who've already heard that, so I'm sorry. Feel free to ignore me for 1 hour if you've already heard that story. So that being said, I'm very interested in going from informal mathematics to formal mathematics and back. And so I have 3 projects that are related to this. I will talk briefly about one of them, and then I will talk more about the second one. So the reason I'll be brief about the first project is because the next talk is all about that kind of thing, and I don't want to just repeat what Yim will say next hour, and will probably be better. So the first, going from informal to formal, is teaching mathematics using a proof assistant. So I've been doing that since 2019 in Orsay, and I've been teaching mathematics to first-year undergrad students, and it's very important to understand that the goal of my course is to teach mathematics, reading and writing proofs on paper. The goal of the course is paper proofs, and the proof assistant is used as a tool and not as the goal of the course. And this impacts everything else. Everything is different when the goal is paper compared to when the goal is the proof assistant. So in particular, there are a number of non-goals in my teaching, like the teaching type theory is not a goal at all. So I never say type, for instance, in this course. Never, ever, and the word type does not appear anywhere. Abstract logic is also not a goal, and expert use of a proof assistant is also not a goal. And all those goals are very nice goals, but they are not my goals in this course. So whatever I will show next, if you think this is stupid because it won't help teaching students type theory, or this is stupid, it won't help students learn how to become expert user of your proof assistant, that's on purpose. So in the beginning, I spent 2 years using Lean, which is the proof assistant that I know, just normally, using the normal Lean input syntax, normal Lean tactics, and the students liked it, and they were good at using Lean for the kind of proofs I wanted to do. But there were 2 big issues. A kind of manageable one and a very disappointing one. The manageable issue was sometimes automation was not at the right level. So sometimes the proof assistant was stupid and asking for details about things that I don't want my students to think about. And sometimes it was too smart, actually, just proving, doing the whole exercise in one tactic, even with carefully hiding the most powerful tactics. I never mentioned, for instance, the simplifier of Lean or the tautology tactic that does just a calculus of proposition automatically. But even hiding those powerful automation, sometimes, for instance, linear arithmetic tactic was doing way too much. And so that was kind of okay. The thing that was not okay was skill transfer to paper. So students were happy proving things with Lean, and then when I asked them to prove even the same thing on paper, so I was asking, you just prove this, say, this could have been, I don't know, maybe the squeeze theorem, or simply a sum of convergent sequences is convergent, or something like this. This kind of proof that I was doing, and they were able to do it on the computer, and then the next minute, when I asked them to write a proof on paper, it was nonsense again. Not for all students, of course, but for some of them. So that was the real issue. So what I did is I developed, very progressively, a teaching library that I call Verbose Lean, which has two big aspects. First, control natural language as an input, and the second aspect is dedicated teaching tactics that were more carefully tuned to do automatically things I don't want to see on paper and ask details about things I want to do I want to see detailed on paper. And so I will show what Verbose Lean looks like, but not for very long, because there is this Rocq Waterproof library that is the topic of the next talk, and was started, roughly at the same time, maybe a bit earlier, with very similar goals, and also sharing a lot of solutions. So in the beginning, it was sharing a lot of solutions because, those were, I'm a mathematician, I was teaching mathematics, and so I had my ideas about what it should look like, and him is also a mathematician, he was teaching mathematics, and he roughly had the same idea about what teaching mathematics should look like, because nothing exotic, and so we came up with a number of solutions that were just the same independently, and then we realized the other ones existed, and we started talking, and that was very fruitful, so we also exchanged a number of ideas and tricks. So quickly, what my version looks like is this. So maybe I will show first where it starts. So this is a Lean file, and this is proving that maybe I should use the mouse to point for Zoom people. So this is a statement saying that if a function is continuous at some point, a function from real numbers to real numbers, then it sequentially continues at that point. And this is the proof term. So if a function f is continuous at x0 and u is a sequence that tends to x0, then f compose u tends to f of x0. And the next three lines, it's three lines because my screen is not wide enough, but this is a single line. This is the proof of this lemma. So you can see function lambda abstraction. So this fun epsilon post maps to, this is a Lean's notation for a lambda abstraction, and then the eliminator of existential, and so on. So this is what I don't want students to write. Okay, then the next example is what I did in the first 2 years. So this is using tactics. So you say it starts intro epsilon post, and on the right-hand side, the Lean answers with the updated tactics state. Can I get rid of this? Click with this. Okay. So, and again, students were able to write this proof, for instance, no problem. But then they stared at this tactic script. And first, of course, the tactic script is unreadable. That's kind of on purpose. It's an imperative tactic script style. So we could do better even with the native Lean syntax. But so they could also look at the tactic state evolving, but that was not enough to make them write good proofs on paper. And so Verbose Lean supports many different styles, and I will go very quickly through them. The first style that you see here, so first the statement is a bit easier to read. The exercise has the title, the data and the assumptions are clearly separated, the conclusion is clearly separated, and that's already a bit better for students, compared to, again, for people not familiar with Lean so much, but I think it would be the exact same in Rocq. For instance, if you want to know where is the statement beginning in that version, you need to see that this column that is here at the end of the line, this is the one introducing the conclusion, whereas the column that is here at HU colon sequence tends to UX0 is just giving the type of HU. So there is a bit of syntax sugar like this, and then some stuff that starts reading like sentences, but it still refers to, it's still very, very closely related to the syntax we had before, and it refers to names of assumptions and so on. And I will skip a couple of variations and get to that version, which is kind of the one that I use with my students currently. So it's the same exercise, but you can see what it says. Let's prove that stuff. Since f is continuous at x0 and epsilon is positive, we get delta such that, and so on. So those sentences are pretty close to what you will write on paper. And I really insist that the goal of this syntax is not to make it easier to write proofs, because it is harder to write. It takes longer. I mean, even when you use tricks to, when you don't have to type every single characters, of course you can use auto-completions and stuff like that, but still, in any case, it's longer to type this proof. And it's harder also because it looks like free form, but it's not free form at all. It's completely rigid syntax. It's just as rigid as the syntax. I don't know if I make any typo. I don't know. I forget this. No, this is not what I wanted to do. Come on. Oh yeah, I remember. I did something. I cheated with something. So I just erase one character, and then there is an unknown tactic error, and it's just completely broken. So the students see it's broken. I mean, the syntax error is a clear message. It says, I don't know what is this word, and so there is not a big problem, but still, I mean, it's easier to make a typo using this syntax than using normal Lean syntax. The point is that when they are trained to write proofs like this on the computer, then you see the effect on paper. And we are trying to, I mean, we hope to measure that rigorously. There is an ANR grant, APAM, led by Cécile Ouvrier-Buffet in Créteil, and we will do experiments, like controlled experiments on students this year and try to measure the effect. And so this is about the syntax. And also, maybe I should say there are different ways to get help about this. You can type all this, but you can also ask for help. So if I type help, I get a message on the right saying you can start a proof by contradiction using this, or also comments like the goal starts with for all positive epsilon. Hence, a direct proof starts with fix a positive epsilon. So you can get help like this. Or you could also just do the proof interactively. I won't do the full proof like this, but if I start the proof, I can just go to the tactic state and select stuff, and then I've got suggestion about what to do. And the suggestion is, I mean, here I've got 3 suggestions. The first one is just a reformulation. Second one is to start a proof by contradiction. Third one is fix a positive epsilon. And if I do that, epsilon is introduced. And then I can select this assumption that f is continuous. I can select epsilon. And then I've got suggestions. And the suggestion suggests to, maybe I can make that bigger. The 3 suggestion is using that the continuity of f and applied to epsilon. The second one is applied to epsilon over 2, and the third one is applied to epsilon plus 1. So students can select the one they want, and then, oops, what happened? Zoom did something. And that's roughly how it works. And you can, in that case, you could write the whole proof by just accepting suggestions, various suggestions. So that's the interface using controlled natural language and various gadgets that we have in Lean to build user interface where you can select stuff in the info view and create suggestions. And by the way, I'm doing all this in NeoVim because I can't stand using bad text editors, but the students, I mean, unfortunately, I don't know what the computer science people are doing at my university, but it seems the first semester is not devoted to learning Vim. So I have to use VS Code with students. I mean, with most students. Of course, we also have good students. So what about automation? So very quickly, so, for instance, this is the squeeze theorem, and so if you've got 3 sequences, and the middle one is squeezed, so the middle one is U, is V, and V is squeezed between U and W that both converge to L. Then V converges to L as well. And so the beginning is very similar, but here there is let's prove that max nn prime works. And when I fix n bigger than max nn prime, the next line I'm saying since n is bigger than capital N here. So you see that one? And here on paper, I don't want to see any detail. I've assumed that n is bigger than max of capital N and capital N prime. I don't want students to tell me that maximum of n and n prime is bigger than n, and by transitivity of inequality, my lowercase n is bigger than uppercase n. So I don't want to see that, or I don't want a lemma that would be called, I don't know, LE of LE max or something like this. And so here just the library took care of it. And in the same way, when I say let's prove absolute value of Vn minus L is less than epsilon, the next step is let's first prove minus epsilon is less than Vn minus L. And again, there is no justification about why this is a good next step. And a bit further down, I prove the other inequality, and that's the end of the proof. And this is, again, something I don't want to say there is a lemma that I apply. And there are no lemma names. So in the full semester, I don't use any lemma name at all in this course. And very, very quickly, why those lemmas are used? So maybe I can set some trace here. So if I ask the lean what it's doing, so on that line, I have verbose lean telling me what it's doing. So it will try to derive those two facts. So for all n, absolute value un minus L is less than epsilon. And the one that I'm interested in is the second one. Lowercase n is bigger than capital N here. And so if I ask for details about this, I've got this tree of traces opening. And the way it tried to prove that n is bigger than capital N, it tried to apply each local assumption, but that failed. You see the cross here says this failed. The linear tactic failed. And then what succeeded is we'll try anonymous fact splitting lemmas. And if I open this trace, you see it tried a couple of lemmas, and it succeeded applying LE of max LE left. And LE of max LE left, the reason why it was tried is because somewhere in the library of this course, the teacher decided to register that lemma. Where is it? Here. You see there is this command, configure anonymous fact splitting lemma, and then I dump a collection of lemma names, and those were decided by the teacher, and those facts do not require any justification. And you can also name collection of lemmas, because otherwise it gets really unwieldy to name everything. Okay, so I think I'll stop here. There are lots of other gadgets, but I think you get the idea. And yeah, you get the idea, and so I repeat it just in case. The goal is not to have an easier to use input language. The goal is really to get students to write the proof I want on paper. So they need to learn how to write proofs on paper. So the proof on the computer should look like proof on paper, and I don't want to see details on the computer that I'm not asking on paper, and I want to see everything I ask for on paper on the computer. So of course it's not completely bulletproof. I mean sometimes sometimes we are very inconsistent in what we ask to see on paper, and so if we are inconsistent, there is no way we can implement this dream. And even if we have a clear idea about what we want to see and what we do not want to see, sometimes my programming is not good enough. Okay, and this is of course all programmed in Lean itself. Okay, so let's move now to the other direction, going from formal to informal. So this is a completely separate project. And the first one I've been doing by myself, I mean, with help from the community, answering questions, especially about programming and meta-programming in Lean. So for instance, without help from Mario Carnero, or Sebastian Ulrich, or Kyle Miller, I would have never been, or Simon Hudon in the beginning of the project, I would have never been able to write all this, but this is still my project. And then with discussion with the team in Eindhoven, with the Rocq Waterproof team. The second part of the talk is all about the joint work with Kyle Miller from Santa Cruz, and it's going from formal to informal. So what's the topic here? The issue is that we don't know what to do with formal math currently in math department. So I've been working in formal mathematics since 2018 or even late 2017, and I've had many coffee break discussions with my mathematician colleagues about this, and it makes for a really great coffee break discussion topic, and that's all. I mean, they find it interesting to discussing it over a coffee, but they do not find it useful for anything, and the reason is mathematicians so don't care that formalization allows to check proofs. And they are very happy with their current system for checking proof, and most of them. Sophie is not happy with the current system. She says no. And the bigger problem is that mathematics is not about knowing that something is true or even that something is proven. It's about understanding why things are true. And if you tell a mathematician that you have a 1 million lines of code proof of something, and they cannot do anything with this proof except for knowing that a computer is convinced that the proof is correct, that is just not interesting information, not very interesting information, and certainly not worth the effort of writing a 1 million line of code. So what do we do with that? So a big issue is that formal math is not readable. And it's not readable in any proof assistant. I mean, I've made tests, and I won't show you comparisons of proof assistant. I mean, it's well known there is one proof assistant whose community is convinced that their proofs are readable, but if you just give them to mathematicians, it's just exactly as readable as the most condensed SS reflect proof you can think of. So it's really no difference at all.
But that's not readable actually. Patrick, it's true you need years of training, but the very condensed SS reflect proof is it's very readable. But it's true you need years of training.
Yeah, okay. If you need years of training to read it, they are not interested. And yeah, but they already spend years learning mathematics and reading normal mathematics proof. So I claim we need a way to turn formal proof into enhanced informal proof. Of course, if you turn formal proof into usual informal proof, then it's even less worth the effort of formalizing anything. So here is an example that I'm always showing. So you don't have to read any of that. It's just so that you see so this is a proof taken for Bourbaki topologie générale. So a very nice and just flawless proof by definition. And so we can try to do something with this, but the issue is there are sentences like we have to show, and you don't know why you have to show that because the target was f is continuous, and maybe the definition of f is continuous is the inverse image of any open set is open, and you don't know any other definition. And the proof does not start with let U be an open set. It starts we have to show that f is continuous at each point x. But this is not the definition of continuity, even in that textbook. So, okay, you need to know why. And also the result no follows at the end. The proof starts with something that is then completely unrelated to the announced target. But then the last sentence, by the way, the target I announced in the first sentence is not done because of some reason. So anyway, if you are the intended readership of this book, there is no problem at all with this book. But if you're a bit tired and you don't understand the structure of this proof, you're just stuck. So let's formalize it. I think I've got a formal proof somewhere. And this is a formal proof of the same statement. And again, I'm showing it to show you that the length of the proof is kind of the same order of magnitude. So it's of course, it's longer than the text that we had before, but not 100 times longer. I guess maybe, I don't know, 3 times longer or something. And then we are stuck because, as announced, this is completely unreadable. And now, what I did with Kyle was to, you can ask OpenAI to explain this proof. So I did not do it recently, but I did the experiment, I guess it was 2 years ago. Maybe it's unfair to show the result today. But I gave a prompt saying, this is a Lean proof, explain that Lean proof to me, and then just paste the Lean proof. And the result is exactly the one you would expect. So it's very impressive looking. I mean, it's clearly some English text talking about topology, and it looks kind of relevant. It speaks of open neighborhoods and so on. And if you try to read the details, it's just completely empty, meaningless. And it also, I don't know why it's kind of repeating itself. And finally, we can conclude, just like students would do. I mean, okay, you don't have time to read this, but if you can watch the recording on YouTube and read that and have a good fun. If you know any general topology, of course, otherwise it's less funny. Okay, so can we do better? And so instead of using a large language model, what about using a programming language? And so I have a programming language that I like, and it's Lean. So I can do, where is my web browser? And so with help from Kyle, I can program my computer and produce this web page. And this web page, it starts the same as my slide. Oh, it's not big enough, or is it? Can you read that? No? So, but that web page was generated automatically from the Lean file that I described. I mean, you need to explain once to the computer how to translate every word, I mean, every declaration name into English, and then the program produces this web page, and at first it looks exactly the same as in my in Bourbaki. There are things like one can see it suffices to prove, and if you don't see it, you don't see it, except that you can click. So first you can see where is the proof going, so you can click on those little ovals and get the proof state, so the tactic state that you would see in interactive theorem prover, and it's written in mathematical English, I mean including, so if we go further in the proof, there are more stuff, and it combines several assumptions from the local context into one line. For instance, V prime is a closed neighborhood of f of x. This was actually the merging two assumptions in the formal proof. But more importantly, I mean, this is already something you cannot do in the textbook. You cannot do on a blackboard, just patiently saying what are the current assumptions, what is the current goal. And it's already very helpful that way. Between any two sentences, you can see exactly the current status. And more importantly, there are those small plus sign. For instance, one can see it suffices to prove. I can click on the plus sign, and I get a whole new paragraph. We see this by the following argument. And then there are explanations, and the explanation contains also sentences like one can obtain, and one can. It means I don't want to explain why. But there is this plus sign you can click. And you click on this plus sign, and you get, using our assumption that y is regular and our assumption that v prime is a neighborhood of f of x, proves one can obtain. So at least it gives you the ingredient of the one can. And, but this is not enough for me because I've forgotten what is a regular topological space. So I click on plus, and I know I get more I've got a lemma name that is mentioned now. And this lemma name, I got access to the name of the lemma, and now I understand why this follows. And if you want to see more details, you can just click on plus until you're satisfied, or if you're a logician, you can click the expand all button. And if you do that, the proof becomes unreadable, just as advertised by people who say you should not write details proof. So the proof is unreadable, and it's not going back to the axioms of type theory. It's still using lemmas and definitions, but expanding everything that was in the formal proof. So I think the biggest expansion is somewhere down below. Yes, here there is 7 levels of expansion. And on those 7 levels, you see it's manipulating sets. Say something like using that f of u intersected v intersected in A is in f of u intersected with A, and our assumption that f of u intersected A is W. There is a lemma. Oh, this is subset trans, so this is transitivity of inclusion that gives me the result. And clearly, that's too much detail. I mean, we don't need to invoke transitivity of inclusion in an informal proof. But that's up to readers. I mean, readers are allowed to ask for all details, and it's not my job as an author to decide on the level of detail. So this is really the key goal of this project, is to produce mathematical text that anyone can read without training, and where the reader decides on the level of details, and the author does not decide this. And I can show you also, so that's a very old example, slightly less old maybe. We also have a system where you can see definition using a system of footnotes. So like, this is just a statement with no proof. So you've got a topological space, and then there is some technical definition, but what I'm interested in is this evaluation map from continuous function from x to r times x to r is continuous, and this continuous has a footnote, and if you click on this footnote, you learn that we equipped this product with the product topology, and you don't know what is the product topology, but there is a footnote here, and so you can click that footnote, and it says the topology is generated by product of an open set in this space and an open set in X, and there is a footnote for open, and it tells you that we equipped the space of continuous function with the compact open topology. There is a footnote to compact open topology, and so on. So there is also a system where you can just unfold definition. And the important point I want to say is that none of this appears in the proof script, because the type class synthesis system is in charge of finding which topology you mean. So, I mean, and it could be the very same thing with canonical structures and unification hints. I mean, it has nothing to do with being specifically the type class system. I mean, the proof assistant is inferring what topology you mean on this product by some kind of magic that the proof author in the proof assistant does not have to care about. But the information is still there somewhere in the system, and so our program can extract it. And now I will use the, I think, remaining 15 minutes to talk a bit about the pipeline and the internal of this Informal Lean program. So the very high-level general pipeline is, so we hook up into the Lean front-end. So Lean front-end is in charge of taking a Lean file and parse everything, elaborate everything, send stuff to the kernel for checking. So, and it's written in Lean, so it's very easy to extend from Lean. Everything is extensible, and everything is here for users. And this project required no modification at all of core Lean. I mean, nothing. Leo Demura was not bothered with by this project at all. Everything is accessible. So then the Lean front end. From the Lean front end, we built something that we call the proof tree, and that's what you roughly imagine. And then we describe statements on proof steps, and this all happens on the Lean side. And then what is generated is a kind of a big dump of data in JSON, and then the display on the web page is using JavaScript, and I mean, as you can guess. So the key pieces on the Lean side. So I won't describe at all the JavaScript side of the project, I mean, because JavaScript. So what happens before, we have like 4 systems stacked on top of each other. The first one is a LaTeX printer for expressions. We need to turn Lean expressions into LaTeX code. And then there is a printer for English sentences or parts of English sentences for statements. We need to render statements into English sentences. And statements that could be the statement of the theorem, but also intermediate claims that appear in the proof. So that's why sometimes it's a partial sentence. Then there is a proof term describer. If you give directly a proof term without using any tactic, we need to do something with it. And then there is a tactic describer, which just handles tactic invocations and builds something. And those are really on top of each other. Every key piece uses the previous ones. So the Lean expressions to LaTeX, I mean, this is really fully Kyle's job. I think I didn't write anything on this part. And by the way, I mean, the project has a bit of a complicated history, and the main thing is still a private GitHub repository. I'm so sorry about that. But that part that I'm showing here is public and has been public forever. I think it's on Kyle Miller's GitHub account. And just so I won't say much about this. Only one thing I want to emphasize as just one point that you need to think about is human beings and the Lean parsers sometimes have different opinions about where you need to put parentheses. And this is just illustrated on those examples. So this is, I'm cheating a bit because in Lean code, we would not write this. We have notations in Mathlib for this, but still, this is valid Lean code, s.sum, fun x goes to x plus 1, and this means sum over x in s of x plus 1, but you can see there is no parenthesis at all in the Lean code, but we need to decide to put parentheses here, whereas for the sum for x in s of 2x, I mean, the usual assumptions for precedence of operations on paper do not require parentheses around this 2x, and so we just don't put parentheses. And the same in the Lean code. So this, hash LaTeX is just the command that we have to test to turn a Lean expression into LaTeX. So this is what you would type in your code editor to get the output on the right. And for this product of sums, the Lean parser thinks that if you put parentheses around this lambda abstraction, then you don't need any other parentheses. It's just not what you would need on paper to disambiguate this. And the last example is about controlling the size of stuff. When you have nested fractions, at some point you start deciding you won't use a horizontal line for fractions, and of course in the Lean code there is nothing like this at all. And the way you define a LaTeX printer, so those are 2 examples. So you need to tell the program how to render your various Lean declarations, and so you define handlers or printers. And for instance, that one is the one that is in charge of printing equality. So there is an annotation, this at LaTeX pp app, so pretty print application of constant.eq, so of the equality relation. And you do, I mean, I won't explain that in details, but you can guess, you get the argument A and B, you don't care about the other one, so there are underscores everywhere. LaTeX pretty print A, called the result A too, because why not? And LaTeX pretty print B, and then those protect right and protect left, they are about those parentheses stuff. So you give some numbers to explain how much protections from neighboring terms it needs, and this is what decides that parentheses are put. And then, okay, I won't comment more that one. And you can see the one for division. It has this smallness parameters, and depending on the smallness parameter, you use frac or tfrac on the LaTeX side, and this is just showing, the A will get some extra smallness, and B gets some extra smallness, and then you return this frac of AB. So it's just no need to understand any details, but just to see what it looks like, especially if you've never seen Lean used as a programming language. So this is all monadic code. LaTeX app printers is a monad, and you see the do notation, and so on. And then I want to show briefly how you go from statements to sentences. And again, don't read any details. I'm just showing the data structures. So just to say there is a notion of a noun, an adjective, an accessory, and then an entity. And an entity has a name. It could have a noun. It refers to local variables. So fvar_id means free variables. So it's the system remembers which free variables are referred to this entity, and you can have an array of adjectives and an array of accessories. And I will simply show what it looks like when you list a sentence. Oh, maybe the rough algorithm is, so when we translate a statement to a sentence, we read the statement, the expression of the statement, and we keep a list of entities that are currently under construction. And for every local variables we choose that appear in the expression, we call one handlers to depending on the type of the variable. So those handlers, they need to be defined by users, once for every definition you have in your library. And then the handler is in charge of deciding what the local variable is about. So for instance, if it sees a type t, it decides this is about t itself. But if it sees an assumption saying u is a neighborhood of x, in my topology proof, it has to decide that this is about u. So this assumption h will enter the description of the entity u. And it does complicated things about dependencies. It can attach adjectives or noun. And so let's see an example of all this. Where is my... Here. So here I've got my statement. So that was the statement of the theorem. And I have activated so I've got the sharp English command to just trigger English translation to English, and I have activated the tracing of the English module. And so on the right, I see the result on the top. So this is the resulting tech code. And more interestingly, I see the trace of what the algorithm has been doing. And so the trace says, okay, it will handle parameter x. And so here nothing very interesting happens. So yes, when it meets this instance topological space x, the trace says I'm using the English param handler for topological space, and it starts looking for an entity describing x, and it found an entity describing x, and this I will open. So now the entity Q now has X, which is an entity providing information about the free variable X and the topological space instance. And now I've got a noun attached that is topological space. And what else? Maybe if I go a bit down below, I will see that the space y now has I want to update y. So the space y now has an adjective, which is regular, and this entity is related to the free variables y, instance prime, and instance double prime, and so on. I mean, you can trace what the algorithm is doing, and in the end, you get this sentence that starts with let x be a topological space and let y be a regular topological space. So you can explore what the algorithm was doing. Okay. And what those handlers look like? So currently, it's a bit hard to write by hand. We need to work on a more user-friendly interface. But this piece of code is the topological space handler. So you can see the trace message that we've been seeing, and stuff like if the entity you found is indeed a type, you can push the noun topological space, and there is a plural text version where you want to see inside a text or inside a text with a plural. And if you found something that was not a type, then what it gets is an accessory. So, this accessory is a topology. Okay. So then I move to describing proofs. So the key data structure that we get from Lean is the info tree data structure. And this is what Lean 4 produces during elaboration. So after parsing your file, it just starts filling all the missing details, understanding what that the objects refer to, and inferring implicit arguments, inferring type class instances, and so on. This data structure provides a lot of information because it's primarily meant for the editor integration. So in particular, it has to handle incomplete input or input with mistakes, with errors. So it's a pretty complicated data structure. It has to cater to the need of autocompletions or things like that we are not interested in all this. So we need to throw away all this stuff. And the information about the structure of the proof is actually not the primary concern of those info tree objects. I mean, it's kind of in there, but it's not the main job, despite the word tree in info tree. So there is still a tree-like structure, of course, but it's not the tree that you have in mind when you look at the Lean file. And certainly not the tree you have in mind when you think of the proof just on paper. So we have a pre-processing step, and we have some intermediate data structure that we call tactic tree, that is much closer to the tree you would have in mind by looking at the Lean file. And then the tactic describers kick in, and they consume those trees, and they create the hierarchical explanations that are then displayed on the web page. And I show you the data structure of tactic describer. So there is a function. So all this is in the describer M monad. So because when those tactic describers are invoked, they need to get access to the current status of the informalization. And so the tactic describer must be able to take a tactic tree and say whether or not they want to handle it. So that's the applicable function. And it also needs to be able to choose side goals. So many tactics produce side goals. For instance, in the proof I showed previously, there was this obtain, and I obtained there exists a neighborhood V in X which is open and whatever. And then what is below is actually a side goal that is the proof of this existence here. And so the tactic describer needs to, the fact that it's a side goal, it's obvious for human beings that this is a side goal that have been created by the obtain tactic. But from the point of view of Lean, it's just, it has a list of goals, and there is no information about being a side goal. This is not the notion that Lean cares about. And so the tactic describers is handle the tactic tree and a potential side goal, and need to decide whether or not it wants to handle that side goal. And then the main thing is a process function. Given the tactic tree and an array of side goals, I need to produce a proof step. And the proof step is just a version of all those things, all those explanations. So the structure of the explanation. So they could be indented blocks, paragraphs, the text with the plus or minus sign to add details or remove details, the clickable words, the tooltips, and so on. And then the JavaScript web app renders this list of explanation. And I think this is what I wanted to say. No, there is no. The proof term describer, do I have 1 minute for this? Yeah, inside the proof, this is the proof term that was rendered with 7 nested sub-steps earlier. This is you recognize there's the transitivity that we saw at the end. Transitivity of inclusion is this dot trans. And for this, we need to be able to do something with such a proof term, and do something and render a hierarchical explanation with this proof term. And roughly the algorithm is, so first if the proof is a local assumption, we say it's an assumption. Otherwise, we collect relevant ingredients. So, and what we call relevant ingredients are either stuff that are explicit in the proof term or instance implicit but proposition valued, so statements that were inferred by instance synthesis of the head function of the proof term. And the first level of explanation is simply listing those ingredients. Remember in the examples, when everything was collapsed, we saw stuff like, or not everything, maybe here, yeah, this sentence, using our assumption that y is regular and our assumption that v prime is a neighborhood of f of x proves, and this is typically something that has been produced by that level of the algorithm. And of course, for every ingredient that is a statement, we just recursively produce an explanation. And we nest those explanations, roughly. And now what we still need to do, so unfortunately the project has been moving very slowly because we've both been very busy, and so the future steps are basically the same future steps than 1 year ago. But so we need to support more tactics. So every lean tactic needs its handler. So of course you can have a default handler, which is just look at the proof term produced by the tactic and use the proof term explainer. But that's a very rough default. I mean, sometimes it works. And we need to work more on handling definitions, but this is in progress. And render multiple files, and render everything that we have in Mathlib and see what breaks. And probably, I mean, something that I think interesting is probably when we do that, render all of Mathlib, we will need to change lots of proofs. Because the way the proofs are written in Mathlib are just mostly very compressed style, and that is not optimal if we do this automatic translation. I mean, the tool tries to render explanations for any proofs, but it's clear that if your the proof you start with was structured in a mathematically relevant way, the output will be better. For instance, the first level of explanation will show the high-level structure of the proof, and if it's messy in your tactic script, it will be messy in the output. And that's all. So, yeah, okay.
Thanks for the very nice talk. I was wondering whether all what you tell us in the second part of the talk is lean specific. So could we, my question is, could there be some abstraction of the, I'm not an expert in this area, so I will say words that are maybe not precise enough, but document model or file model that you're expected as input, so that would be a lean file, a Mathlib file in this case. Could we abstract this to apply it to more proof assistance?
So I think that the part that could be abstracted is at the other end of the pipeline. I mean, the explanation starting from here, the data structure of nouns and stuff, how sentences are rendered. I mean, there are people who've been working forever on this kind of thing. I mean, in linguistic, or I think there was a talk yesterday. I'm sorry I was not here about this grammar things. I mean, those people they know a lot more, and we kind of try to understand what they are doing, but we still did our own stuff in the end. It was easier, but that part, I mean, in principle, it should be better if we use, and for instance, our stuff is really targeting the English language. I mean, doing that in French would already be a nightmare, and I know there are languages where it would be much worse. I mean, our sentences, of course, they already don't look so great if you're just, probably if you're a native speaker. But in English, it's kind of okay. In French, that would be much worse. And we have no abstraction at all of which language is used. So that part is completely, I mean, if you redo it better somehow, it should become a proof assistant irrelevant. But the beginning of the pipeline, I mean, we're really using the introspection capabilities of Lean, and that would be, I think, very prover specific, because we really need access to the internals of Lean. We cannot take the proof script as a string
Sure, but that's precisely my question. My question really was not about this end of the pipeline. My question was, what are you expecting from your interactive theorem prover to be able to be an entry point for this?
So I need to get access to all the information that has been elaborated, and that is not in the proof script, but was just inferred by unification or whatever. And I need also access to which tactics were used. So if you only give me the proof term produced by the tactic, I cannot do anything with it. I mean, the powerful tactics, they produce completely inscrutable proof terms, and this I cannot do anything. So I need to get access to also the sequence of tactics as syntactic object and as expressions in Lean. We also, I think we currently don't have examples, but in principle, we could decide to rerun the tactics and even, I mean, swapping for custom tactics. If there is a tactic doing something powerful quickly, but it's not leaving enough trace of its work, we could, during rendering, just use a different tactic, or maybe the same tactic but with different tracing options activated to get access to more information. So we currently don't really rely, at least not seriously, on this possibility, but I suspect that for the most powerful tactics we will need this.
Thank you for the talk. I was just wondering, is it a goal of your work, once it's more mature, to make it extensible to external users, in the sense that if I write a tactic, will I be able, is there an interface for me to describe how this tactic is
sure.
informalized?
I mean, it's all in user space, so those tactic describer. So I have not shown a tactic describer, but you can just write them in your code. I mean, that's kind of always the answer with Lean. And yes, you can do it in user space. I mean, that's the whole point of Lean 4 compared to Lean 3, right? So Leo Demura got tired of users asking contradictory things that he had no time to implement, so he just made everything user implementable.
Thank you. Actually, I was considering using Lean as kind of thing, but finally I didn't. And actually, what seemed to me kind of wrong with Lean, and probably it's not wrong, it's just a question, that it's kind of magic, right? Exactly, if you don't teach type theory, they don't understand how Lean works at all. And so it's all look magic, right? And you want, maybe if you want, right, to make things kind of clear. Of course, if you, how to say, things like your plus, right, you can go deeper, but at least classically you're supposed to to reach some firm ground. Maybe we should abandon this idea, but yes, if you
so
have any...
you're talking about the first part of the talk for teaching, or you're talking about the...
Yes, it's not about first
So
part.
in the teaching stuff, I said that there are different styles that are supported, and if you use if you use this style, I mean, you're really in control of a lot of things. You say by HF applied to epsilon using epsilon pos. I mean, this is really a very thin wrapper around the proof term. I mean, it's just. I mean, you could also say you could remove the word applied to epsilon using epsilon pos, and that would be a valid proof. And you see, no, the proof term is no longer hidden, and that small proof term. So you can use this style if you feel that this is useful to students. And I mean, really, my journey has been very progressive. In the beginning, so I never used the first style, just write the proof term. I never asked my students to write this 3 lines long proof term, but I did start with with just a normal tactic like this, where you control everything. But then I realized this is not what I wanted to teach. I mean, what I wanted to teach is what I want to see on paper, and it's already a lot more rigorous than what you get just if you don't use a proof assistant. And all those. I mean, all those proofs, I mean, if you ask a first-year student, at least in this country, to write a proof of this statement without the help of the computer, just nothing happens at all. And they do not start at all. And one of the things that will teach students, and by the way, there is a French version. I mean, there is also a big multilingual support part of the library, so I do not ask French students to write anything in English. Of course, that would be a disaster. But they, I mean, especially first-year undergrads. But so they learn that if the proof starts with, the goal starts with for all positive epsilon, they need to write a fixed positive epsilon, soit epsilon and positive in French. And already this is a huge win. I mean, and just if you spend 12 weeks teaching using a proof assistant, and the result is that students know that when the proof starts with a for all, they need to fix something. It's already a tremendous success. And the students, I mean, I was at a meeting a couple of weeks ago, and the person in charge of our first year of study told me, "Oh yeah, students love your course, and they understood that they need to write soit X and Y réel if the goal starts with for all." I mean, so I don't know. Maybe I didn't answer the question, but I mean, there is kind of, you know, when this is the actual goal, I mean, thinking about do we really reach the foundations and do we need to teach type theory is kind of disconnected from my reality, at least. In the beginning, I spent time apologizing for the using type theory. Like I was telling people, yeah, it says X colon real number and not X belongs to real number, but that's just a funny notation. And then, I mean, after 2 weeks, I realized that the students were not bothered at all by this, and just any time spent discussing this was completely wasted. Again, in this context of teaching mathematics to first-year undergrad in mathematics. Not really, because, I mean, they were taught mathematics, not logic. So they were taught, maybe if they ask some teacher what are the foundations, I mean, mathematicians know they are meant to answer and mumbling something about set theory. But I mean, just, I don't know, presumably lots of you work in computer science department, but if you just go up 2 stairs and find mathematicians and ask them to just give you one axiom of Zermelo-Frankel, and you get no answer at all. I said 2 stairs up. You're cheating, so don't ask Sophie. I said random mathematician.
So you've spoken about syntactic errors when writing proofs, but what would happen if a student would write the part that is not about syntax? For example, after the HF, if they mess up the hypothesis, what would you tell them at this point?
So first, the statements, they never write in my course. It's kind of a choice. I mean, there is enough to do proving stuff. So the exercises, all the statements are written. That being said, they still need to write stuff. Like for instance, if they write since U converges to L, I mean this U converges to L is a Lean expression that they need to write, and I mean if they get this wrong, there is an error message. I mean we can try removing I don't know removing this S and it says unknown identifier and unexpected token. And I mean, there is a syntax error. I'm not sure I'm answering.
Yes, but for example, I don't know exactly how to pinpoint you to what I mean, but when they write, for example, I don't know, h in prime to point for n, etc. This is an hypothesis that they should not have to write in a proof assistant because the proof assistant would understand what they introduce, but there they have to write it. And what would happen if they mess up it?
Actually, they don't have to. I mean, you can remove the end of this. No, in this case they have. I mean, in some cases they don't have to write it. But yeah, I mean, if they for instance, if I remove this prime here, then they get an error message too. I mean, they get an error message saying that the system could not prove that fact. So it could not prove this. Maybe it's clearer if we look at it on this side. And here there is the tracing that is, of course, they don't turn on tracing during the course. So the error message would look like this. Could not prove there exists n prime, and it tells you which assumptions were used to prove that. Which is not the full local context. I mean, all those given facts is what have been announced. W converges to L and epsilon is positive. Those were the what was after since, and all the data that enters those facts. This is all listed, and then from those things, the system was not able to prove the goal. And I've been thinking maybe this year I'll be working on this, using a counterexample generator to give a counterexample. We could do that. That would be a bit of work, but that's something I consider doing.
Yeah, so the Malika purpose is to bridge the gap between informal and informal proof. And so, do you think that this course we're talking about can be a smooth introduction to formal proof that may help changing mind about the use of proof assistant, as you mentioned? I think. I mean, do you have feedbacks of students because even if it was not the main goal of your course, maybe it helped them to have interest for formal reasoning, formal proof, and maybe it helps them to read later these unreadable proof you mentioned. Do you have feedback about these facts?
So, no, I don't. So I really don't advertise formal methods as that much in this course. I mean, we're really focused on mathematics and what they need to do on paper. And it is extremely rare that I have students doing formal method after this course. I mean, even the students who are really happy with this course, and there are quite a few of them, they just continue doing mathematics. I mean, I think since the beginning, I had exactly one student who really became a Lean expert user, and this is Anatole Dedeker. And Anatole is about as much of a random student as Sophie is a random mathematician, so that's not at all an indication of anything that he's doing formal methods. And so no, I'm not. I'm really not using this at all as a way to recruit students in formal methods. I mean, I've been teaching, for instance, at CMU. I spent a year at Carnegie Mellon University in Pittsburgh teaching proof assistants for the sake of teaching proof assistant, and there I've been training students to work in formalized mathematics, but not at all in this course. And I never tried to convince mathematicians that they should start using Lean by telling them you could write very simple proofs using this controlled natural language, because that was not the goal. I don't think it's really easier to start using. I mean, really, the goal is not to make it easier to write lean proofs. The goal is to make it easier to write paper proofs for students who do not yet know how to write paper proofs. I mean, learning to type intro instead of fix or soi is just, this is not what is difficult with proof assistance. And simply...
I mean, there were many questions. There is one question online, by Marco Ceveto, which is, how do you see possible connections with, LLMs and, like, let's say, machine learning? Since you have now some kind of, nice connection to English, let's say, even if it's controlled, do you see any possible extension or?
Yeah, I mean, so I'm assuming this is on the second part of the talk, and I can comment on the LLMs with the first part of the talk. I mean, it's very useful that internet is not full of proofs written in this verbose lean language, because students who simply want to cheat using ChatGPT, simply nothing happens. I mean, there is no, the sample of, there are some proofs on GitHub, of course, this is all public, but not the solutions to my exercises that I use with students. So that's very good, that large language models are very bad at verbose lean, and I think that's the same with Waterproof, because this gives a chance to learn to students. I mean, you don't know this because all of you've been happy and very lucky to learn before AI, so you were able to just grow a brain and everything. But for students nowadays, it's much harder to learn anything because they always have this temptation of not learning and just hoping to cheat with LLMs. So that's on the first part. But the second part, of course, the output of verbose lean can be used to train language models doing the work in the opposite direction, and this will happen. I'm not specifically interested in that. What I hope is that if some AI agents start really proving stuff in Lean, so right now what they produce is either complete garbage or correct proofs that are complete garbage, because they are just unreadable proofs, but I mean much more unreadable than the usual one, with unnecessary steps and complicated things. So if it stays like this, there is nothing we can do. But let's say they become better at writing lean proofs, but still we don't understand the proof because when you get a proof script in Lean, it's very hard to understand. And then if we can have informal Lean turning those into something we can use, that would be great. But this is science fiction for now, but that could happen.
Okay, wonderful. I think we gave a lot of time for questions after your beautiful talk. So we can thank Patrick again. Yeah.